Okay, I realize most of you have already finished this homework and reading guide for 3.1, but I wanted to go ahead and give you a short video, and I'm not going to concentrate on everything like all the different number systems, just the differences between them. So a number here, it's an idea or abstraction that represents a quantity. Now a numeral is the written symbol. So we think in our mind how much something is, and then we use a numeral to write down what it is. And we put all these together and we get a numeration system, which is what we use to count by. So the earliest numeration systems appear to have grown just from tallying. So when you make tally marks, I'm sure you've done this before. Once you get to 4, you do that to make it easier counting. So here we're regrouping at 5s. Now, because we have 10 fingers, it's really easy for us to regroup by tens, which is the number system that we grew up with. Okay, and in most numeration systems today, grouping is done by tens. And because it's grouped by tens, the names of our numbers reflect the grouping process. So here's a couple examples. I thought these were neat. 11 derives its name from medieval German phrase ein Liefon, which means one left over. So 12 is 2 over 10. Now I'm not even going to try to pronounce that. So what we have is a base 10 numeration system. If we decided to regroup every time we got groups of 3s, we'd have a base 3 system. Computers operate on a binary system. So they regroup at 2s, because the only thing a computer can do is be on or off in any one position. So those are the only 2 digits. So if you were to ever read computer code in machine language, it's going to be 10101010, kind of look like the matrix. Now, the book does talk about some different numeration systems, and I want to point this out because Egyptians used an additive numeration system, right? So what they do is when they just would repeat a symbol as many times as they needed. Okay, so they might have 3 shepherd's sticks and someone I don't even know. I can't even remember what the symbols are. You obviously will not have to know that. But they would just repeat the symbol. Now, if we had to write 1, 1, 1, 1 over again, it would be a pain. Or if I wanted to represent 81 as 9 nines, okay, just as like by repeating the number 9, it becomes a pain in the butt. But they also had a base system, so their symbols were still powers of 10, but it didn't matter what order you wrote them in. Okay, so that's why it's called an additive, because I could put the thousands, whatever represented thousands, I could put that first, and I could put whatever represented ones next, and then whatever represented hundreds next. It didn't matter. Now what we use, forget this example right here. I should have taken this out. What we use is based on the Hindu Arabic numeration system. So the Hindus invented it, but the Arabs transmitted it to Europe through trade and stuff like that. So we only have these digits that we use, and we regroup after we get groups of 9. Okay? So the digit in the numeral has a name that indicates its position. So here is the number 75,063. So just by telling where it is, it matters that I put the 10,000, then the thousands, then the hundreds, then the tens, and then the ones. Okay, so it's a place value system because the place matters. Okay, and this is the expanded form. So 7 is in the 10,000s place, so it would have a value of 7,000. 5 is in the 70,000. 5 is in the thousands, so it would have a value of 5,000, and so forth. Okay, so we wrote the number in one type of expanded form by writing 7 times 10,000 plus and writing each according to their place name. But another common method is, instead of using each of those numbers, the long versions, we can use the powers. So these are all powers of 10. 10 to the 0 power. Well, anything to the 0 power is 1. Then we have 10 to the first power, which is 10. 10 squared, which is 100. 10 cubed, which is 1,000. Okay, and notice that's a 1 followed by 3 zeros. And then this would be 7 with 4 zeros, 70,000. So this is just a shorter way to write that using exponents. Okay, so again, what we have is a positional numeration system. It's not additive. We don't write the same number over and over again. What we do is, wherever the place the digits put in, then you know how much the value is in that place. So here are some examples. Okay, here we got 7,024, and I want to know what place the 0 is in. Now we always, on a whole number, imagine that the decimal is right there. So we always count ones, tens, hundreds. Okay? So the value of that digit is 0, and the place value is the hundreds. In number 2, the value here, now that value is 0. We could say it's 0 hundreds, but that doesn't make any sense. 0 is 0 regardless. Here the 7 is in the 10,000s place, so the value of the 7 here is 70,000. And again, in number 3, the 2 is in the hundreds place, so the value of that 2 in this number is 200. Now, writing numbers is something you probably did, but probably not for a long time. Have you done this in school? Okay, but there are some things I want to point out. So, we know all the single words, 1 through 20. Okay? Now, 21 to 99 are usually compound names. Okay, and they're hyphenated, except for the number 30, 40, 50, 60. Okay, so those multiples of 10, we don't hyphenate those words. But like 31, there's a hyphen between the 30 and the 1. Now, even when the names are part, like I say 31,000, that 31 still has a hyphen in it. So we need to remember to always use the hyphens where they're needed. And then there's another important thing. So if we write this number 347, 347, notice that there is no and here. It's common for people to say 347, but the and is reserved for a decimal point if you have to read that in your number. So do not use the word and when you're writing a whole number. And as you know, you're all familiar with, every time we have 3 digits, we use a comma to separate those. Okay, and these are called the period of the digits. So if it's hundreds, one period, thousands are another period, 10,000s are another period, and so forth. So within each period, the digits are read as we would read any number, and then the name of the period is recited. Okay, and I didn't put this example, but I just wanted to remind, because there are examples in the book, I just wanted to remind you that do not use the word and make sure you hyphenate compound words like 31, 42, 55, and so forth. The next important thing I wanted to remind you of were rounding rules. So I'm not going to work any examples. I think you all know how to round. But what you want to do is, if you're going to round, you want to locate the digit with the place value to which the number is to be rounded. Okay? Then you look at the digit to the right. If it's 5 or greater, round it up. Okay? And then fill in the rest with zeros. If it's 4 or less, keep it the same and fill in the rest with zeros. I would have people who would say you have 39,560. And I want to round that to the nearest 10,000s. So here's the 10,000s place. The 9 tells me that that 3 needs to go up to 4. And some people would stop there and just write 4. Well, that doesn't make any sense. This is why we have to fill in the zeros. If you had $39,560 in the bank and all of a sudden the bank said, oh, we rounded it so you have $4, does that make any sense? I mean, if I only had $4 after I put almost 40,000 in there, I would be really mad. In fact, someone would be answering some questions. So we have to fill in the zeros. Now, to model our base system, we use base 10 pieces. Okay? And all bases, different bases, but regardless if it's base 10, base 5, base 3, whatever, are the first place is always a unit digit. Okay? Now we group by tens, so we have 10 to make a long. Okay. And then we put 10 of those together to make a long, to make a flat. And then we can repeat that flat and we have a long flat. So this is 1, tens, hundreds, because it's how many squares are in this thing, thousands. So if I'm going to make base 10 pieces to represent 536, I need 5 blocks for the hundreds, 3 blocks for the tens, and 6 units. So here are my 5 hundreds, 3 tens, and my 6 units. Okay, now they talk about a bundle of sticks model where you use 10 sticks to make a bundle. So you count individual sticks, then a bundle is 10 sticks, and then you can have bundles of bundles. But the base 10, I think, is a little bit easier. Okay, so what we can do is we use those bases to regroup. So here's an example. Okay, so what would I need to replace this? I mean, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, So if I take 10 of these, right, I'm going to get another long. But I have 2 of these left over. Now, if I have 10 longs, they become a flat. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these become a flat. And I'm drawing with my mouse, so you have to forgive my drawing. So I'm going to end up with 3 flats total. There aren't enough flats to regroup. And then the 2 longs, and then my 2 units. So this would be what's called a minimal collection. Here I got a lot of extra pieces. Here's the smallest number of pieces I can use to represent that collection. So that's base 10. Here we have base 5, okay? And just like I said, in the units place we always just have a single square. And what we're grouping by determines what our next ones look like. So when I put 5 units together, I get a long. And when I put 5 of these longs together, I get a flat. And when I put 5 flats together, I get the long flat. So the base here, now if I were in base 3, I'd have a unit. I'd have 3 of those units to make a long. I'd have 3 of those longs to make a flat, and so forth. So we have this problem. Sketch the minimum number of base 5, so make sure you look at the base 5, to represent the following number of units. Okay, so I have 39 units here, right? Now, let's take the biggest thing we can out of here, okay? Our flat was 25 units, but I need 39. If I add another, or add a long, there's 5 more, so that's 30. Add 5 more is 35. And now I have 4 left, which can only be written as units. Okay. And then here's the solution. Sorry for my writing. If I had a way to erase it, I would have. But here's our 25, 30 together, 35, and then 39. Okay. Now, so we had our long, our unit, our long, our flat, which is 25 pieces. Sorry about that. And the 5 of those 25s is going to be 125. Okay, so I can't use one of these long flats here because I only have 115 units. So let me get as many out that I can in 25s. So 4 25s is going to give me 100. Okay, then I have 15, so I can only go by 5s here. Okay. So that's what it would look like. $327. Now I can use that big long flat, which is 5 25s or 125. So I can pull out 2 of these 125s. So that gives me 250, and then 275, 300, 25, 26, 27. Now, positional numeration works regardless of the base. So just as we had powers of 10s when we're in base 10, we have powers of 5s when we're in base 5. Okay, so 39, which we represented as 1 flat, then we had, 2 longs, and then we had 4 units. So it's 1, 2, 4. So these are our units. Our what we would call tens place, but it's really our fives place, and this is our 5 squared place. Sorry, I've got this messed up, but I don't want to have to record this. So if we take 115 like we just saw, where we had 2 long flats, 3 flats, 0 longs, 2 units. Now notice in both of these we say what the base is. If the base is 10, we don't have to write the base because that's our common base. But if it's any other thing, you have to tell what base it is, or you don't know really how many units that consists of. Okay, so I hope this helps. Sorry about it being kind of messy, but thank you.